Okay, we are going to look at the TPs from section 9.1. You were told to do on page 88, after I had done these in the video, you were told to try these. This was your first set of TPs, and so here are the answers for 6, 7, 8, 9, and 10. You were supposed to have done these on the calculator and see what was happening. 6 converges to 0, 7 diverges to infinity, 8 converges to 1, 9 diverges by oscillation, and 10 converges to actually this, which is the number E. This is something you need to know. E is the limit as n goes to infinity of 1 plus 1 over n to the n, or you could write this as n plus 1 over n to the n. Either way, you need to know that. That is a very important number for you to know. And then the second part of your section 9.1 TPs was on page 89. I did the first two problems for you, and you were supposed to do the others. So in problem 3, when you just listed a few terms out, you got 2, 4, 2, 4. Okay, so the limit as n goes to infinity of this sequence diverges by oscillation. This one, you could use your exponent rules that you know, and so this converges to -1/2. Number 5, this one requires some work. It actually requires L'Hopital's rule because as n goes to infinity, we know the derivative of natural log of x is 1 over x, which is always positive, which tells us the natural log function is always increasing. So as we go to infinity, this goes to infinity, and so does this. So the question is, which one gets there faster, the logarithm function or the polynomial function? Because if the logarithm function gets to infinity faster, this goes to infinity and diverges. But if the polynomial function goes to infinity faster, then this goes to 0. Well, we can use L'Hopital's rule. Since the numerator goes to infinity and the denominator goes to infinity, we have indeterminate form, and we can use L'Hopital's rule, which gives us 1 over n over 1. This is no longer indeterminate form. And so as n goes to infinity, this converges to 0. So what did we just learn? That a polynomial function increases more rapidly than a logarithmic function. All right, this one is a really important one to know how to do. What we've got to do is we've got to change n plus 2 factorial. N plus 2 factorial is n plus 2 times n plus 1 times n factorial. Now I can cancel the n factorials. That leaves us the limit as n goes to infinity of 1 over n plus 2 times n plus 1, which converges to 0. Nice problem. So number 7, we need to approach in a similar way, except I need n minus 3 factorial, so I'm going to use the numerator and take away 1. N times n minus 1 times n minus 2 times n minus 3 factorial. Those cancel. That leaves me the limit as n goes to infinity of n times n minus 1 times n minus 2, which is infinite. So this diverges to infinity. In section 9.2, there is a problem from the video that I told you to write down and that I would do this in class. Well, we're not having class. So you should have written down, show that the harmonic series, this one, diverges. All right? Well, the limit of the nth term is 0. So we know my nth term goes to 0, but my nth term test for divergence says if the limit of the nth term is not 0, the series diverges. It doesn't tell me if the limit is 0 that it diverges or that it converges. We have to do something. Well, let's look at this little and break it into partial sums. Okay, so the sum of our first term is 1. All right, the sum of two terms is 1 plus 1/2. And this is where it gets interesting. The sum of 4 terms would be 1 plus 1/2 plus 1/3 plus 1/4. Now, what we know is I can look at 1 plus 1/2, and here's what I know. 1/3 is greater than 1/4. So if I were to put 1/4 here, then would it not be true that 1 plus a half plus a third plus a fourth is greater than 1 plus a half plus a fourth, which we know is 1 plus 2 over 2, right? 1 over 2, 2 over 4, 1 plus 1. All right. Let's look at the sum of my first 8 terms. My first 8 terms would be 1 plus a half plus a third plus a fourth plus, following our rule, 1/5, 1/6, 1/7, 1/8, and let's do what we did up here. We know that this sum is going to be greater than this sum, where I have replaced my 1/3 with a fourth, and I'm going to replace 1/5, 1/6, 1/7, all with 1/8, because we know 1/5 is bigger than an eighth, 1/6 is bigger than 1/8, 1/7 is bigger than 1/8. And what's nice about this is I get 1 plus 1/2 plus 1/2 plus 1/2. So this sum is 1 plus 3/2. Notice what we have here. This was 1. The sum of 2 terms was 1 plus 1/2. The sum of 4 terms was 1 plus 2/2. The sum of 8 terms was 1 plus 3/2. What do you think the sum of 16 is going to be? Well, we're going to go through the same process all the way up to plus 1/9, 1/10, 1/11, 1/12, all the way up to 1/16. And we now know that this is going to be 1 plus a half plus a half plus a half plus a half, which is 4/2. So look, 1 plus 1/2 plus 2/2 plus 3/2 plus 4/2. So we would see that the sum of 32 terms is obviously going to become 1 plus 5/2. The sum of 64, I'm seeing a pattern here. The sum of 2 to the n terms, this is 2 to the 5th, 5/2. Okay? 2 to the 5th, that's a 5/2. This is 2 to the 6th, 6/2. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So you can see our pattern is the sum of 2 to the n terms will be greater than 1 plus n over 2. So as n goes to infinity, your sum goes to infinity, so my series diverges, the harmonic series diverges. That's just a beautiful little proof. I will leave this here for you for a moment so you can copy it down. It is definitely something to be pondered. And now we're going to go to the TPs from section 9.2. So that example we just did, here we're looking at it here. The sum of my first term, that you were given the series was 3 minus 9/2 plus 27/4 minus 81/8 plus 243/16. That was your partial sum. So we are going to look at the first term adds to 3. The first 2 terms, the partial sum of 2 terms is 3 plus 3 minus 9/2, negative 3/2. The sum of 3 terms is 3 minus 9/2 plus 27/4. Well, we know what 3 minus 9/2 is, plus 7/4 gives us 21/4. 4 terms is 3 minus 9/2 plus 27/4 minus 81/4. We know that these 3 have a partial sum of 21/4 minus 81/8 gives us negative 39/8. And finally, the sum of 5 terms is 3 minus 9/2 plus 27/4 minus 81/8 plus 243/16. We know already that the first 4 terms add a negative 39/8, which with common denominator gives me this, which gives me 165/16. And here are your decimal sums. So on number 13, we're supposed to determine if this series converges or diverges. You will note that the nth term is not 0, it's 1. So the series diverges by the nth term test for divergence. Number 25, you should recognize this. I have something to the n power. as a geometric series where my common ratio is 3/4, so the absolute value of my common ratio is less than 1. So this series converges by the geometric series test. 35, you are told to find the sum. Well, when we factor that, we can see that we need to use partial fractions. So I'm going to separate this fraction by a over n plus 1 plus b over n minus 1 using the Oliver Heaviside method. Getting my denominators to be common allows me to set my numerators equal, so when n is 1, this term will drop out and b is 1/2. When n is -1, this term will drop out and a is -1/2. So now we can rewrite our fractions. I'm going to bring 1/2 out and I'm going to switch the order of my fractions. Okay, so I'm going to list a few terms. 1/2, when n is 2, that gives me 1 minus 1/3, plus when n is 3, gives me 1/2 minus 1/4, plus when n is 4, 1/3 minus 1/5, plus when n is 5, 1/4 minus 1/6, when n is 6, plus 1/5 minus 1/7, and you can see that this -1/3 cancels with that +1. This -1/4 cancels with that +1. Okay, this one -1/5 cancels with that +1. So you can see all of the remaining terms except for this one and this one are going to drop out. So we get 1/2 times 1 plus 1/2, which is 3/2. Answer is 3/4. Really nice. And finally, number 4, we had a repeating decimal. First, we want to write it like this. And then we want to realize that this would be 0.4 plus 0.04 plus 0.004 plus 0.00004 and so forth. So forth. So forth. So funny. I'm entertaining myself. So I can see that my common ratio is 1/10. My first term is 4/10. I have a geometric series with my ratio having an absolute value that is less than 1. So this series converges, and I can find the sum using my sum of a geometric series formula. Substituting a 1 minus r 4/10 over 9/10, the 10s cancel, the sum is 4/9. Okay, I hope that was helpful to you. 9-1 and 9-2 lots are due Friday for our class. Okay.